All right. So,
in the library.
more great news.
Sarcasm on my part.
Yay.
Chapter 4, Part 1. Waiting on you. A week from today.
This problem set's got 11 problems. Take about 90 minutes to complete. Got a week to work on it. All right. The other thing is the problem set for Chapter 3, Part 2 is due tonight. Most of you, at least, have got a good start on it. Several of you completed it. 5 of you haven't touched it. So you got something to do tonight. So that's where you're at. Okay. So we're going to continue and keep talking about Chapter 4, which we just barely started. So I'm going to go back to the introduction slide. Topic is chemical quantities and aqueous reactions. And some textbooks split this into 2 separate chapters. This author put this as one long chapter. This is one of the longest chapters we'll do this semester. So likewise, we'll do a lot of calculations with it. We'll spend more time with this one than some of the others. We're going to talk a little bit about global warming and maybe the contribution that's coming from fossil fuels. Certainly regards climate change today. Back into the chemistry side of it, reaction stoichiometry. We're going to introduce limiting reaction, reactant, theoretical yield, and percent yield. Then we're going to talk about ways to distinguish between different solutions, introduce what's called solution concentration and stoichiometry. How we deal with aqueous solutions and some of the solubility rules, what precipitation reactions are, as long as some other classes of reactions that we have. Reactions that happen in water we call aqueous reactions. And then we have acid-base and gas evolution reactions. You actually have done both of those in the lab in the first experiment that you did in another class called redox reactions, reduction oxidation reactions. More problems at the end of this chapter than any other chapter I'm going to give you to take a look at. Okay, so again, those are things that you can study on your own time. Okay, so the last thing that we did in class was talk about the population change that we had. And in our 1 hour and 15-minute time frame yesterday, the world population increased by approximately 11,300 people. Now, the reason that becomes significant is we look at today, want to consider one of the most important scientific decisions to make is the influence that greenhouse gases are having on our environment. And in particular, is this something that is man-made, and we can undo what we've made if it is a man-made problem. So greenhouse gases, the concern is that there are certain gases that as the energy comes from the sun, these gases, instead of when the sun's not shining on the earth, that energy could be emitted back into space as the earth rotates around. But if the gases are surrounding or high enough concentration that are the greenhouse gases, they effectively work as a blanket, absorb that energy, reflect it, or trap it in our atmosphere. So that's the concept that we have. The concern is how much of this contribution is man-made. We know climate change is something that has happened before human population on Earth has been significant. We know that ice ages followed by heating periods have happened dozens of times. Almost the entire continent of North America has been covered with sheets of ice, going all the way down to Mexico, and the ice has receded and came back and receded. And those are the things that carved out things like the Grand Canyon and all of the geographical features we have of our country today. The concern is on the short term, there seems to be a significant change that's occurring that suggests that there is a contribution for mankind that's playing a role. So if we look at the change in temperature that's being occurred in the atmosphere, there's the change in temperature that we're talking about is not huge. We're talking about less than a degree change in 100 years. So the question is how delicate is Mother Earth? Is a degree change going to make a huge difference? And why would we think that mankind plays a role in that? Well, one of the things that we look at is during the same period of time that the CO2 concentration in the atmosphere has increased approximately 25%. So going back to the 1860s, the CO2 was about 290 parts per million in the atmosphere. Today, it's knocking 400. 25% increase. And you can see that the rate that it's increasing, and it's not increasing slowly. If we look at where it's going to be in the next 50 years, we think it'll be well over 5. Okay, because it's continuing to grow at this steeper rate. One of the things that's changed is other countries are now starting to consume energy in a way that they hadn't before. What are the most populous countries in the world? What's the most popular country? China. What's number 2? India is number 2. China and India represent well over a third of the world's population. Right? And both of those countries, going back 50 years ago, had very little energy consumption per person or per capita. Now, the thing that's changed is they decided they like air conditioners and cars and computers and lights and all the other amenities that developed countries like as well. So what's happening as those countries have started to consume more energy per person, that's the reason this curve made this shift up. And it's honestly probably going to continue to make a shift up. The thing that we can offset it a little bit with is have higher efficiency devices. We choose a car that gets better gas mileage. We use light bulbs that are LED light bulbs that don't consume near as much energy, more energy efficient appliances, homes, etc. So if we look at what the change has been, and this has been the controversy and still the controversy. So here's the plot in the change in global temperature. It seems to go up with a somewhat corresponding value as the CO2. And the question is the CO2, this change, indicative of this change? The CO2 concentration, we can say probably to some degree of probability is coming from mankind, but we know in the atmosphere, just like the ice age has changed, CO2 levels have went up and went down. Okay, a volcano erupts. It blows out billions of tons of gases. And among those gases are sulfur dioxide and carbon dioxide. And those are classic greenhouse gases. So there's been the CO2, if we go back in a broad historical term, not just a couple hundred years, CO2 concentrations have been going up and down all over the place. But in the local, this is the concern now. What are we doing and what can we undo? And here's another slide, and this is something that you don't see very often. It's a lot of different pieces of information. This shows at the bottom, starts looking at the rate that we consumed fossil fuels worldwide, and really at the start of the Industrial Revolution, that's starting about in the 1900s, that's starting to increase, and we're starting to use these things more and more and more. And the reason this is important because the consumption of all fossil fuels lead to the emission of CO2, carbon dioxide in the atmosphere. And we consume a lot of gasoline per day in this country. When you look at it annually, it's staggering. We'll do a calculation with that in a minute. You can say the same thing for the amount of coal, the amount of natural gas that's consumed. But it's not just this country, because our population is not near as high as some of the other countries in the world that consume as well. Okay, some other terms that we can look at to monitor or compare this term to. So this is basically our CO2 emission. So this is the CO2 from mankind, humans, right? So that's our contribution that we're making. This is glacier shortening that's been measured. All right, this is the sea level rise that's been measured, going over to the 1850s or so. Here's the change in temperature according to the U.S. Census Bureau. If there is an uptrend line, it's minor. Okay, it's not as high as the increase that's suggested from the global change, which shows the upshift in the last 40 years or so. There's another measurement that's been done scientifically for Arctic temperature, and it's went up and down. Northern hemisphere temperature, it's a little bit more flatter, but it's got the change here. Now, the top one is one you never see talked about in all the discussions about global warming. All of our energy comes from the sun. Okay, except for nuclear energy. Everything that we have, wind energy, solar energy, fossil fuels indirectly come from the sun. So this is how much the solar activity can shift. And if you look at this hump and this increase, the sun's playing a role too. So the sun goes through quiet regions where it's not emitting as much energy off. Okay, so if you were, one of my hobbies is astronomy, and I set up telescopes. I set them up for the eclipse day out for the student union, first day of class, and a lot of people looked at the telescopes, looked at the sun. There was a couple of sunspots to look at, which has been odd, because the last 8 years the sun has been deadly quiet. You look at a telescope and you go, oh wow, that's a fascinating orange ball. There's no sunspots to see on the surface. It's only in the last 2 or 3 months that we started to see some changes in solar activity, seeing some solar flares and different things that we typically see. And it's on a pattern. It goes up and down for the sun's emission. These, as these energies fluxed in solar activity, that has to have a direct impact on the Earth. That's the amount of energy striking the Earth. So it's more, that's what makes it such a confusing question. How do we fix it? Do we literally spend billions upon billions of dollars to reduce CO2 emissions? And that's a choice that honestly has to be discussed in your lifetime. So there's going to have to be a decision made. Do we let nature take its course? Sea levels continue to rise. Places like sea levels rise 5 foot. Miami, you won't go to Miami Beach anymore. You'll go to Orlando Beach. Okay, and if you know the geography, Orlando's 40 miles inland. So sea levels rise 5 foot, you lose a lot of the coastal areas in the continental United States. So is that going to happen? That's the question that we don't know. Could we take all of our CO2 right now? We have the technology to take all the CO2 that comes from a coal-fired power plant and trap that as a block of ice, dry, solid carbon dioxide. And one of the theories is you take it out to the depths of the ocean and you drop that block of ice off into a trench in the ocean that's miles down, and the temperature and the pressure would keep it indefinitely in the form of solid CO2. So it wouldn't come bubbling back out to the surface. The problem is, you as the consumer are going to pay for that. It would probably triple your electric bill. Okay, so we have the technology to address this. Problem is, can we afford to address it? Would it make any difference? Would it make any difference if the population in the United States did this, with our 225, 30 million people, when we just saw the world population is 7.4 billion? If the rest of the world didn't do the same thing. So, those are the types of things that you're going to, in your lifetime, be making critical votes about the people that you put in Congress, the people you put, I'm not even going to talk about the White House, but wherever it's going to be. So if we look at why it's become more significant, this is a plot of how human history has changed, the world population in human history. So this is the population that are alive at any period of time, and this is not a linear scale down the bottom. So this is going back 1 million years or so. So the earliest relatives to man, there are literally a couple 100,000. A few million, maybe. And it's staying that way until about maybe 4,000 or 5,000 BC. Then maybe population hits a minimum, and finally it's climbing and climbing and climbing, and we get to like 1 AD. So we're going back 2,000 years. We're still only a couple of 100 million people on the face of the earth. And then we have this boom in the population explosion. So it starts increasing kind of steadily, and then we hit through the Dark Ages. We actually have a significant decrease. About 1 in 5 people on the face of the earth died during the bubonic plague, Black Death. Right? It decimated Europe. Okay, 1 in 2 people died in Europe, but that influenced the world population so significantly. Then we come out of the Dark Ages, science comes into play. Finally, we start to do science and apply science to our daily lives. We learn how to do a few things. We learn how to extend human life. We learn how to provide energy so we can support larger populations. We start to learn the first crude things about medicine, disease, and prevention of, how to do better crop growth. And you look and see what's happened to world population. So it's after the 1800s when we get our first population of 1 billion people. And then you look at how it's changed and the rate that it's growing. So here's another slide that shows you where we're at. So it was around 1800 when we got our first billion people. It took 133 years for world population to reach 2 billion people, around 1930. It took 33 years to reach 3 billion people. 15 years to 4. 12 years to 5th. And I remember in class, 6 billion people. We did that as a celebrated that day in class. A few years back, we hit 7 billion people. Now we're at 7.4. And we're climbing over 10,000 people an hour. So if you think about how much that's changed, it's doubled in your parents' lifetimes, the world population. That's doubled in your lifetimes. Is it going to continue to double? Will it double in your lifetimes? The rate of growth is slowed down a little bit, but it's not changing that much. I mean, it's still just getting after it in terms of the increase in world population. Here's the craziest fact to me that's ever hard to work. Understand what I'm saying? There are more people alive today than have ever died throughout human history. Because of the population explosion, there are more people breathing air alive today than have ever died throughout human history. There have never been 7.4 billion people die. That's hard to comprehend. Every person that's alive, if you want to think of entitled to, needs some energy. Okay? Whether it's energy that comes from the natural resources, firewood, they pick up firewood, they're going to need food, depending on your standard of living, and this is where there's a big difference in inequality that's changing. In the United States, we have, and through most of Europe, have a much higher standard of living than 75% of the world. But that 75% of the world has now realized, that's not such a bad life they have. So the competition for energy is going to be stronger in the future. So that's just something I want y'all to think about. It's a lot of people on this little blue planet. Okay, so how many people are there? Surely you're going to get that. A couple of you are waiting on it. Give me an answer. All right, we're on with 22. All right, so thank you. Yes, there are 7 billion people here today on the face of the earth. So, I'll let that do what it's supposed to do. confinement. All right. So one of the reasons that you should be concerned is the sources of CO2 in the environment. Oops, one. Go back to the highlighter. And what can we do about it? Does it matter? So one of the things we get CO2 from is the combustion reactions from fossil fuels. But again, another critical source is things like a volcanic eruption. There was a scientist at the University of Arkansas that came to Southeastern to speak almost 20 years ago, and I hosted the reception for him at our home. His name is William Faley. Dr. Faley's expertise was measuring remote emissions of gases. So he was actually in this area because he worked with Texas Instruments and Raytheon, developing sensors to go on the back of airplanes that they can fly over a battlefield and they can tell what gases would be used, in particular whether nerve agents or other chemical reagents. And until I haven't seen the plane flying about 10 years ago, for about 10 years, but they had an old DC-9 prop plane that flew out of Grayson County Airport that looked like it had a big tail behind it, dragging behind it about 20 foot long. And that was actually the array sensor for the technology that he had developed, and the military was incorporating that in different devices. They would fly over, first thing they would do was take the plane out to calibrate it. They would fly over the nearest patch of cows they could find. What do you think they were looking for? Methane. They're looking for fresh cow piles. Okay, because they could look at the methane emission, that's how they would calibrate their instruments. And then they could take it and do their different measurements. What Dr. Faley became famous for was he developed the sensors to set up on the volcano to shine a laser across the volcano, hit a mirror and bounce back, and from that he could measure the amount of gases that were being emitted from that volcano. The first time they successfully did this, they were measuring sulfur dioxide emissions from a volcano in Hawaii, and had an unexpected burp happen. So the volcano had an eruption, and his instruments there were to capture it. More sulfur dioxide was emitted from that volcano in 1 hour than all mankind puts out in a matter of a year. So sometimes volcanic eruptions can be enormous in the amount of gases that they can emit to our atmosphere. All right, so how do we judge whether or not we're the significant contribution? That's the debate that's the real question. I mean, I'll tell you that I'm just a personal opinion, and it matters. I'm certainly not a climate scientist, but I've wavered back and forth a couple times based on the evidence I've saw. Can we even stop this, or is this just something that's going to happen? Right? And I'm not sure where I'm at now. The thing that I think to stop it is it takes a worldwide commitment. Every country has to get on board with it. At least I think we need to be having the discussion as occupants of planet Earth, and not just thumb our noses in the air at possible ways to find solutions. So can we judge this or not? One thing we can look at to see what our contribution is we can look at our model compound that we use to represent gasoline, and that's octane. So you've got an octane rating at the pump on your gasoline when you choose, are you getting unleaded, super, or whatever the highest grade is. I'll never buy anything but the cheap stuff. So, and you're not saving any money if you do. It doesn't help you out. That I know. It reacts with oxygen. 2 molecules of octane react with 25 molecules of oxygen in the air to produce 16 molecules of CO2 and 18 grams of water. So like we talked about in the previous chapter, it's a combustion reaction. A hydrocarbon reacts with oxygen, and the emitted products, the reaction, are CO2 and water in this particular reaction. So what we call reaction stoichiometry is the relationships between all the reactants and all the products in terms of the number of molecules, which we can translate into the number of moles that are consumed and produced in a chemical reaction. So if we look at the CO2 emission, I'm interested in what is the relationship between the CO2 that might go into the atmosphere per the octane that's going in. And I can see the fact that this is a 16 in front of the balance reaction. tells me there are 16 CO2 molecules produced for every 2 molecules of octane that are consumed or burnt. Okay, so that gives me a relationship that I can use. So if we look in chemical reactions, every substance is related to every other substance by these relationships. And it has to obey the law of conservation of mass. We've looked at in a couple of labs. We're actually applying that in our lab tomorrow as well, even though we're using it for a different concept overall. And we know from what we learned in the last reaction, we have to balance the number of atoms to make an equation balance. That's an application of the law of conservation of mass. You don't make matter in a chemical reaction. All you do is break bonds and form new ones. So the study of the numerical relationships between the species that are consumed and produced in a chemical reaction, the term for that is stoichiometry. So we have to learn how to use stoichiometry when we look at a reaction. So now what we can look at is these numbers that we put in front of as coefficients in front of the different reactants and products to balance our equation. Those represent the relative number of moles that are being consumed and produced for that particular reaction. Okay, so it tells me that there are 2 molecules, and wherever it says molecules, you can substitute the word moles, because I can go from moles to mass and mass to moles. All right? So 2 molecules react with 25 molecules of the O2 to form 16 molecules of CO2 as well as the 18 molecules of water. So the stoichiometry for this reaction is what's down here at the bottom. It's 2 octane, 2, 25 O2, 2, 16 CO2, 2, 18 water. So now I've got a relationship. If I wanted to know what was the relationship between octane and oxygen, it's 2 to 25. If I wanted to know what is it between oxygen and water, it's 25 to 18. I've got those coefficients telling me the mathematical relationship between any reactants or products in that system. As long as I've got the balanced reaction, I'm there. Now I'll tell you, when we do these types of things, on your next test, I'm going to give you some balanced reactions. And I'm going to tell you to balance this reaction. If I don't tell you to balance the reaction, I'm giving you a balanced reaction. Okay? So we're going to learn a lot of other things where we need to apply equations. So you don't have to worry, is this reaction actually balanced or not? If I give you something with coefficients, it's a balanced reaction in front of it. Okay, so we're going to apply this to concept of stoichiometry to making pizzas. Occasionally we make a pizza at our house. So if we think about pizzas, you can go from mild to wild in terms of what you want to do with the pizza, but you need some dough or crust, you need some tomato sauce, and you need some cheese, and you can make a cheese pizza. It's that simple. When I was, my kids were in middle school or grade school, they walked them as a class group to Domino's, and they all made pizza at Domino's. You have to make their own pizza, and then they brought the pizzas back and they ate them in the school cafeteria. Ever since that experience, make pizzas at house occasion. The ratio that they use for the ingredients, or at least with this recipe, is 1 crust with 5 ounces tomato sauce, 2 cups of cheese. That's the contents to make 1 pizza. So in the same way that we could take this recipe to make a pizza, we could apply that as a mathematical stoichiometry. 1 crust for 5 ounces of sauce, 2 cups of cheese, yield 1 pizza. Okay, so if we wanted to think, well, how much pizza could I make from 10 cups of cheese? Then I could look at the relationship, and I know if I had 10 cups of cheese, it takes 2 cups of cheese for a pizza. I can do my same type of dimensional analysis with canceling out units. That's enough cheese to make 5 pizzas. All right, so that very simple concept. But we can do the same thing when we think about doing it with molecules now instead of ingredients to make a pizza. We just need to think about mole to mole or molecule to molecule conversions, and we use the balance reactions to look at these particular relationships. Okay, and the coefficients that are in that balanced stoichiometry become our conversion factors to relate the moles of one substance to the moles of another substance. So if I looked at my ratio that I have for the octane combustion, I know my stoichiometry relationship is 2 to 16 for the relationship between octane and CO2. Okay, so that becomes my conversion factor that I can use to relate those two different substances. Okay, so if I want to put that to a calculation, let's say I consume 22 moles of octane. How many moles of CO2 do I form? So to answer that, I need to know my balance reaction, and I've got that. We went over it about 8 times so far. I look at my relationship between those two particular substances. Here's the octane. Here's the CO2. And it's a 2 to 16 stoichiometry. And then you start with what you know on top. I've got 22 moles of octane, so I'm going to write that on top. My relationship is that there are 2 moles of octane coming from here per 16 moles of CO2 coming from here. The moles of octane would cancel out top and bottom. I'm left with moles of CO2. Those consumption of 22 moles of octane produce 176 moles of CO2, carbon dioxide. Okay, so from that, I've got a way that I can take the amount of a reactant and predict how much of the product is going to be made. And in this case, if it's combustion, CO2 is a gas, so that gas goes straight to our atmosphere. Right? So we've got a way that we can look at these relationships. So here I want you to look at a relationship. So I'll give you a balanced reaction. This compound's pentane instead of octane. And I want to know how many moles of CO2 are produced when 3 moles of pentane react with excess oxygen. And do this on your own. You've got a minute. And 21. Fifteen seconds. Any more answers? 7 more answers. Last chance. Get your answer in. Okay, so most of you thought it was choice C. All right, so let's see if it was choice C. We're not going to find out. Ask a friend. Do it again. Same question. Consult with somebody and see if you think his choice C is correct. So at least 30% of you thought it was something different than choice C.
30% of the class would do it.
That's not stupid, and I remember those two.
Okay, answers in. All right, so everybody went with C. So, yep, it's C. Let me just clarify where C comes from and show you how to set this up. So you would start with what you have in the problem. So I've got 3 moles of pentane, and that's the pentane. So I've got 3 moles of C5H12. I use the stoichiometry from the reaction. 1 mole of C5H12 per I've got excess oxygen. I want to know how many moles of CO2 per 5 moles CO2. The moles of pentane cancel out. You got 15 moles CO2.
Why was the exit on?
Say again.
Why'd you underline exit on?
Well, it means the oxygen is not the limiting factor. There's extra of this. What I'm going to run out of is the pentane, and that's going to limit the amount of product. And we're going to talk about that in a moment. That's called the limiting reagent or reactant and reaction.
So the stoichiometry is just a ratio.
It's a ratio, yeah. It's like in the dimensional analysis or factor analysis. It's simply the relationship between those two terms in the equation. And I kind of hinted to this when we were talking about this back in chapter 1. So much of what we do this entire semester is these relationships. Setting up units, getting units to cancel out will take you so far this semester in telling you're doing a problem right. So again, I encourage you to continue to do that. Okay, we can use these relationships to do a lot of different things. So in particular, we use them things like conversion to go from molecules to mass to moles. So if we look at how much gasoline we consume annually, in 13, that's the most recent estimate I have available, the amount of gasoline or equivalent of octane, we burn about 3.7 times 10 to the 15th grams of gasoline. It's a bunch of gasoline. Okay, to give you an idea, about 20 ocean tankers arrive to the United States every year or every day to deliver to deliver crude oil. We only import about 30% of oil. So we're burning hundreds of tankers of loads. And each one of these tankers has got 1 billion barrels of crude oil on it. It's just an obscene number that we consume of gasoline per day. And that's not counting the coal and the natural gas that we burn in our power plants. So I'd like to take this number to try to figure out what's the mass of CO2 that mankind is producing. So the strategy I'm going to use is take the mass of the reactant A, which is the octane, convert it to moles, use the stoichiometric relationship to get it to moles of the gas, the product we're interested in, which is CO2, and then finally go from moles of CO2 to mass of CO2. And we know our relationship, molar mass, is how we convert between mass and moles. The coefficients of the balance of reaction is our current conversion factor we use here in the middle step to go between the two different species. And then finally, to undo the moles into mass, we're going to use the molar mass of CO2 again. Okay, so here's how we would take a look at that. So I take my mass of my reactant. All right, so we know from our relationship that the molar masses of octane, if I do the math on it, so 12.01 times 8 plus 18 times 1.008 for hydrogen. Octane weighs 114.22. CO2 weighs 44.01. And the relationship to the balance reaction is 2 to 16, as we said before. Okay, so we know how to do that. So if I take and plug this into the equation, I'm going to set the whole thing up across here. I'm going to write in smaller writing so I can get it all in here. So we've got 3.7 times 10 to the 15th grams of octane, C8H18. All right, the molar mass is 114.22 grams of C8H18 per a mole of octane, C8H18. Okay, I know that there are 2 moles of octane. Per 16 moles of CO2. And then finally, my last step would do 1 mole of CO2 144.01 grams of CO2. O2. Again, I'm going to check my units before my math before I do any math. So moles of CO2 cancel out, moles of octane would cancel out, grams of octane would cancel out. The units I'm left with were grams of CO2, which is what I'm looking for. So I think I've done it right. And if I do the calculation on that, I find that the consumption of that, this is 1.1 times 10 to the 16th grams of CO2 that we kick into the atmosphere every year. 10 to the 16th is just a freaking large number. Almost unimaginable how large that number is. That is a tremendous amount of gas. And if we put it from all the other sources that we consume, if you add all the coal and the natural gas that we burn, so fuel that we use to heat our homes, the diesel that goes into larger vehicles going up and down the road, we're kicking closer to 10 to the 17th grams of CO2 in the atmosphere every year from what we consume with human consumption. It's a very, very large amount. So can we account for that curve going up based on what we do as humans? Yes. Without a doubt, we know that we can have a direct correlation in the fossil fuels that we consume and that CO2 production, at least in the short term. Long term, if a volcano blows, let's see, wherever the island of Bai is, I think it's Bai that's got a huge volcano that they think is going to erupt in the next few days. They've evacuated some 150,000 people that are near that island. If that thing goes off, it may completely disrupt what we put in, maybe 10 times more than what human consumption or production is. We don't know. Okay, we know things like that. Mother Nature has its own way of doing things. Okay, so let's look at an example of something that's maybe more applicable to you as a person. Let's say that you have something that has some sugar in it. So 9 grams of glucose. Consume 9 grams of glucose for whatever that source is. And glucose reacts with oxygen inside of our body. We breathe it in. It produces CO2 and water. So we get energy out of it. So the thing that's missing here is plus energy. That energy gives us the fuel to drive our muscles, and that allows us to move. But in that, we produce some water. And I want to know in a combustion reaction, and it wouldn't matter if I were doing the reaction inside of a chemical vessel to do it, or if you were to eat it and it happened inside of your body, it's the same reaction. Okay, I want to know what's the volume of water that's produced. So just give you how many grams of glucose is not a common sugar that's found in things like a soda. Anybody got a canned soda? Anybody drinking a soda? Water. Healthy tea. Good for you. All right. So a 12-ounce can of soda has got about 40 grams of sugar. Okay. So 9 grams, 2 big gulps, quarter of a can. That gives you an idea of how much sugar that corresponds to. Okay, so what the strategy I'm going to use to do this calculation is go from grams of sugar to moles of sugar. To do that, I need the molar mass of glucose. And if I calculate it out, I find it's right at 180 grams per mole. Then I'm going to use the stoichiometry to go from moles of glucose to moles of water. That's a 1-to-6 relationship. And finally, I'm going to use the molar mass of water to go back to grams of water. And then go from grams of water, I need to go to milliliters. The relationship between mass and volume is the density. And the density of water is 1 gram per milliliter. Okay, so it's just a dimensional analysis problem is what it comes down to, a conversion factor. So always start with what you're given. I've got 9 grams of sugar, so that's going to be the first thing I'm going to write down. All right, and then I'm going to do my conversion. The glucose weighs 180 grams per mole. The authors felt like they needed to put that in scientific notation, so that's the way it is. The stoichiometry is 1 mole of glucose per 6 moles of water. So 1 mole of glucose per 6 moles of water. Now I've got moles of water. 1 mole of water weighs 18 grams. And then finally, I could use the density, 1 gram of water per milliliter. And if I look at my units, what happened in the dimensional analysis, things cancel out. Grams of glucose and grams of glucose cancel out. Moles of glucose and moles of glucose cancel out, top and bottom. Moles of water, top and bottom cancel out. Grams of water, top and bottom cancel out. I'm left with milliliters, which is way back what the question asked for. When you eat that 9 grams of glucose, you produce 5.4 milliliters of water, which you're either going to either sweat out, breathe out in your air, or would urinate out. So everything that you consume in, if it's a combustion reaction for a fuel, you breathe the CO2 out and you produce water. Okay? So you can actually survive without water for a fair amount of time if you eat the right fuels. Okay? Because some fuels that you eat more than others, so like glucose in particular is oxygen hydrogen rich, they produce water as a byproduct. So that's one of the things, protein in the long term, you need for muscle deterioration and to maintain healthy muscles. But if you need your short-term sugar fix, I mean, when I go out and ride a bike, and on the days when I'm riding with people, we may try to do a 50-mile ride. And depending on what type of shape you're in athletically, and I'm not, I use all the free sugar that's up in my body in about an hour and a half into the ride. And I'm dragging. And you've got these, they're kind of the energy drinks for somebody that needs a sugar fix. We can take this thing that's just a sugar paste, basically, with some flavoring in it of whatever your choice is. And you can squeeze that tube of stuff down when you're actually riding your bike, and all of a sudden your blood sugar goes back up, and you start to get some instant energy to go with.
So like honey?
Say again?
So it's like honey?
Well, honey is complex sugars. This is the simplest sugars. So it's things like glucose. When you take a complex carbohydrate, and honey is kind of an intermediate. So if you look at something like look at example for a corn plant. I did a project with a group from the Lane USDA lab years ago, and we looked at how the sugars inside of a plant, in particular, they were looking at sweet corn, how the sugars change as that plant is maturing. So when the corn is developing on the cob, it makes the sugars, while the corn kernel is still soft, it makes the sugars into glucose and fructose, simple sugars that the body can very, very rapidly metabolize. And right before the plant starts to completely harden, okay, it takes those and bonds them together. Glucose and fructose make sucrose, which are what's most soft drinks. And then it links those together to make a change of starch. So when you get a hard kernel of corn, the corn is in a complex carbohydrate called starch. So for your body to metabolize that sugar and get the energy out of it, it's got to break it down. And there's actually enzymes inside of the saliva in your mouth that start to, when you take a bite of food, immediately start chewing on it, chopping it down more in your stomach. But the smaller pieces of sugar, you can get the quicker energy fix out of. Now, also, the bad side about it, if you're diabetic, the smaller pieces of sugar jack your blood sugar way up. So that can be detrimental if you don't have good control in your body of your insulin, which regulates your sugar levels. But it's something that, sugar is something that you need all the time. Okay, so this is a similar type of conversion reaction. This is what happens in an airbag. Have any of you been in a car where an airbag went off? Could be the first class I've ever had that had. You have, okay, all right.
Hi.
You may not want to raise your hand to that, okay? So I can understand that feeling. So when an airbag goes off, there's a chemical in the airbag called sodium azide, and it's a solid. And when an electrical charge goes across it, it converts to a gas almost immediately, and it's that gas that inflates the airbag. Okay, so you've got a certain mass of sodium azide. You've got 6 grams of sodium azide. I give you the molar mass of the sodium azide. I give you the balanced chemical reaction, and I'm wanting to know what's the mass of nitrogen produced when that reaction goes off. So try to do this individually. Give you a couple minutes to do it. So you can't just start with the 6 grams of sodium iodide and then just do a dimensional analysis. One relationship at a time. Okay, can we approach you and answer? Seconds. Okay, take a guess at this point. All right, so we're less confident on this one, but the predominant choice is choice A. Yeah, you can talk about it. Answer it again.
You set it up.
Let me try it. It's 2 and 3, I go 1. So I see what X is.
Well,
3 and 2.
it mainly is dealing with the ion channels and the regulation
And
flow
then
of
we're trying to
water
get
across
grams.
the cells. So that's what's happening in the diuretics. Usually diuretics are to help extract water out. Typically, that's well, it could be related to blood pressure problems, to heart disease, to a lot of biological processes that cure. Sometimes it's a combination of
3 to 2.
and what makes it more significant is our body is almost 80% by water by man. So we've got a lot of water all the time. And when you retain water, it really can make a huge difference in terms of your ability to move around.
Because doesn't creatine hold water?
Yes. Okay. Oh, well. Okay. You've discussed. Vote again. Three people haven't voted. Last chance. All right. So everybody's convinced this day to show you how you would set the problem up. Start with what you know. You've got 6 grams of sodium azide. Sodium azide weighs 65.01 grams of sodium azide per mole. For 1 mole of sodium azide, the stoichiometry says that 2 moles of sodium azide react to form 3 moles of nitrogen gas. 1 mole of nitrogen gas weighs 28.02 grams of nitrogen gas. Let's see if I've got my units set up right. Moles of nitrogen cancel. Moles of sodium azide cancel. Grams of sodium azide cancel. That's looking good. And you get 3.88 grams when you go all through that now. All right. Question on that? We'll start doing calculations like this in most of the labs that we do. We'll take a mass of a reactant and we'll use that to predict the mass of a product. Okay? So after this week's lab tomorrow, that'll be a standard thing you do. When you do organic chemistry next year, you'll do it with every lab you do. You'll calculate how much product you should get. All right, let's go back to our pizzas and think about our pizzas again. So we said with our pizzas, the ratio was 1 crust to 5 ounces of sauce to 2 cups of cheese. That makes a pizza. So I've got 4 crusts in my fridge, 10 cups of cheese, and 15 ounces of sauce. I want to know how many pizzas I can make. So the concept that we need to find out is what is the limiting factor? Call that the limiting reactant or the limiting reagent. All right. So what we need to do is look at every reactant and find out, or every component or ingredient in this case, and find out how much pizza it could make. So the ratio for crust is 1 crust per pizza, so there's enough crust to make 4 pizzas. We've got enough cheese, 10 cups of cheese, 2 cups per pizza to make 5 pizzas. But if we look at the tomato sauce, there's 15 ounces of sauce, 5 ounces per pizza. We can only make 3 pizzas. So the limiting factor, limiting ingredient in our pizzas is the tomato sauce. When we think of that in the chemistry terms, we call that the limiting reactant or the limiting reagent. It's what's going to make the reaction stop. So we have to identify what component is it. Okay, so frequently we react 2 things together. Sometimes it's more than 2. But what is going to produce the fewest moles of product? Okay, so if we, this is just pictorially of the same thing that we just talked about. So look at that. We think about the tomato sauce as our limiting reactant. Now we could take that relationship to the limiting reactant to find out how much we can make. And if we think about our pizzas, we call it the theoretical yield in terms of a chemical reaction. So if it's everything together, unless I have a big spill in my preparation, I'm going to make 3 pizzas out of it. Okay, and if we apply that same concept to our chemical reaction, we can predict what the yield would be of a product to be made. We simply compare that of the limiting reagent, the stoichiometric relationship, to find out how much product can be made based on how much of that limiting reactant it is. So we call this term the theoretical yield in a system. So whenever we have multiple reactants that can occur in a reaction, typically you're going to have one species that's going to be consumed before anything else. Once that reactant's used up, the reaction is going to stop because there's no more product that can be made. So therefore, this reactant that limits the amount of product is the one we call the limiting reactant. And again, we sometimes call it limiting reagent. So usually a reaction is going to go to completion to the point where that particular species is consumed. Now, not every reaction goes 100% in the forward direction. You'll learn about that later in chemistry, so it's more of a Gen Chem 2 topic. It depends on the particular reactant. But there's typically going to be one species that's not consumed completely, and that's called the excess reactant or reagent in excess. So from the limiting reagent, we can produce or calculate a theoretical yield. How much of the product should I make? All right. So if we look at going back in our relationship to pizzas, if we drop one on the floor, you spill some before it gets in the beaker when you're doing a chemical reaction. Maybe we only got 2 pizzas out of the oven to put on the table. All right, so what happens in life and in chemical reactions, we have an actual yield that represents what we get at the end. So by doing a comparison, a percent yield is a ratio of the actual divided by the theoretical times 100. That's percent yield. It's your actual yield divided by your theoretical yield times 100 as a percentage. And what would the range of numbers be that you could have? It could be, when you're doing percents, what's the range of numbers you could have? So if it's not between 0 and 100 when I do this calculation, something's wrong. So it's going to be between 0 and 100%. So ideal world, we're living close to this 100% number. Sometimes it's not that high. Let me show you, I want to show you an example of a drug. And I'll tell you the story behind this guy. Okay, so here is a compound. Its chemical name that's sold on the market is Taxol. And here is its structure. So magnify that up. So it's a complex component that is found in nature. There were actually a group of botanists that worked here at Southeastern, and their names were Taylor's. Connie Taylor still alive. The husband has passed away now. They were herpetologists. They collected plant species from the United States, but they also went all over the world and collected plant species. There was a room down where the nursing program is in the 60s and 70s that was one of the most comprehensive collections of leaf species anywhere in the southwest United States. They had 250,000 different plants cataloged. NIH paid them throughout the 60s and 70s to travel all over the world. Their focus was South America and to identify new species. And then they took those new species and they would take them back to send samples of the plant material back to NIH, and NIH would catalog them. And at some point, NIH was starting to look at them for medicinal properties. So in particular, in the 1980s, somebody is doing an essay on some leafy substances that came from a tree. In particular, it came from the Pacific yew tree. And he's doing a screen, doing all these different assays to find out what it has resistance for and works. And they find out that there's a compound in this particular bark of this plant that inhibits breast cancer. Right. So they start to look at this particular thing, and they isolate, this is the compound in it. So Taxol is its common known name. And the NIH says, oh my gosh, this is possibly one of the cures to breast cancer. They put out a reward for the Pacific yew tree. Guess what plant is now extinct in the United States? Pacific yew tree. Because every logger in the United States realized that that tree, if he cut down a Pacific yew tree, it was worth 100 times the next tree he cut down. We have eradicated the Pacific yew tree from existence. Before we synthetically learned how to make it, Taxol wasn't used as a drug. Most insurance companies today still won't even cover the use of Taxol. You have to pay for it out of pocket because you're talking about something that is going to cost you on a chemotherapy usage for later stages of breast cancer. So if everything else they've tried is not working, Taxol is kind of a last resort drug because we haven't got the cost down enough. Initially, it was costing anywhere from $5,000 to $20,000 a dose, and you're going to take anywhere from 5 to 10 doses of that drug.
And that's after it became.
Well, that's what the companies, everybody hogged up what they could get. Then we learned how to synthetically start to make it. So that's a tricky structure. It took the organic chemist about 4 years to finally figure out how to make this sucker. It's 23 different chemical reactions. You go the first material to the next material and you get step 1. You do that 22 more times. Each time they did the reaction was anywhere from a 60 to 80% yield. And we talk about percent yield. That's the reason I want to talk about this. When you do that 60% yield 23 times, you take 0.6 times 0.6 times 0.6 times 0.6. You do that 23 times. They were literally starting with 100 kilograms of material to get a gram of product. That's the reason that particular drug was so expensive initially. Today, we've learned a trick. We've learned how to take pieces of this molecule and clone it into E. coli. And we find things in nature that make something that looks like this portion of the molecule and maybe this ring structure. And basically, we have code that in using biotechnology into E. coli. Basically, you feed E. coli some amino acids and it poops this stuff out. You harvest those products and you put them together, and through 3 chemical steps, now we make Taxol. And the cost of Taxol now is down to like $1,000 a dose. Right? It's became we've learned how to harness nature, but we eradicated that plant. That's one of the things that we don't know what we've lost. And the thing, just going back to percent yields, even though you think about, well, I'm just going to get a 80% yield. If it's in one step, that's good. But if it's in a large number of steps, even 60 to 80% is detrimental. We want to try to keep those numbers as close to 100 as possible in any system. Okay, so summarizing limiting reactants and yields. So we have a limiting reactant. We also call it the limiting reagent. It's going to control in our systems the amount that we can produce. The substance that's in excess is called the reactant in excess or the reagent in excess, and there just needs to be more that's required than the limiting reactant. It doesn't matter if it's 0.1 times more or 5 times more, as long as it's in excess. All right, there's some extra of that particular compound. The theoretical yield is the amount that's predicted to be produced by the reaction based on the amount of the limiting reactant. The actual yield is the amount that actually is collected from the product. And the percent yield is the ratio of what you actually produce divided by the theoretical times 100. Okay. The words on those 2 slides are something you need to get familiar with. We're going to start with doing calculations on these starting on Monday. We're going to apply these to a variety of reactions. You've got like 6 clicker questions. We do this on Monday. Okay? A lot of calculations. I encourage you to look over this chapter, be prepared. I'm going to let you out 2 minutes early because I don't want to start this new unit and be dead in the middle of a calculation. Okay, see you in lab tomorrow.